Okay, this is the team-based learning day 1. We're going to be talking about the chemical senses, namely taste and smell. So here we go. So taste buds are composed of 3 types of specialized epithelial cells. And so the 3 types of cells are the gustatory cells, or the taste cells, and these are the actual taste receptors, not the neurons, but they're the taste receptors that stimulate the neurons. And so these have several gustatory hairs, or little microvilli that increase the surface area of where they come in contact with the chemicals that they perceive. and um, and so these cells have taste pores, which are um, little holes and little channels that a little hair extends through, and the chemicals come down through that little channel and interact with that hair, and that's what stimulates it. And these cells have a very high turnover rate, only about 10 days, and then they are replaced by a new cell because they're in contact with lots of strong chemicals all the time. So they get cell death occurs quite frequently. So then there's also supporting cells, which these are kind of giving shape to the taste bud. And then we also have basal cells, and you're going to find a very similar setup in the nose and the olfactory cells as well. They have these 3 types of cells. The basal cells are stem cells that are there to replace the taste cells after they die. And so on the tongue, we have these bumps on the surface called papillae. And on the background of these slides are a type of papillae. So it's a electron micrograph picture of a tongue is actually what the back of this is, and that title slide is showing that. So these little bumps that stick up, and they give the tongue a rough texture. And most of them contain taste buds, but there's a certain type that they're called the filiform papillae that do not contain taste buds. So if you can see there under types, we've got 3 types of papillae. One is the filiform. These are very small. These are the ones shown in this background here. These don't have taste buds, and they're just there to provide friction on the tongue. And then we have the valate, or the circumvallate papillae, which are very large, and we only have about 7 to 12 of these on our tongue. But each of these have about 100 taste buds in them. So they form a V kind of on the back of the tongue. And then we have the fungiform papillae. These are much smaller, they're round and much more abundant, but we have about 5 taste buds in each of these. So here's a picture of the tongue, and we can see here's the valate papilla. These are the larger ones that have around 100 taste buds each, and then you can see the fungiform papillae all throughout here. And those are the smaller ones that have less taste buds in them. And if you get a close-up view of one of these valate papillae, you can see there's lots of taste buds within one of those papillae. So the taste bud itself is kind of gourd shaped, and in case you don't know what a gourd is, this is what it looks like here. It kind of has a larger bottom and a smaller top. The taste pore, which would be kind of on the top up here, is where the chemical comes in, and then that opens up to the surface of the epithelium. And then the gustatory hairs, which are part of these gustatory cells, stick up through, and they're covered in saliva, and that's what interacts with the chemicals to stimulate these cells. We find these mainly on the tongue, but we also have taste buds on our soft palate, which is like the roof of your mouth and towards the back, towards the posterior part, inner sides of your cheeks, as well as the pharynx and the epiglottis, all on the back of your throat. You also have taste buds as well. So here's a slide looking at the structure of a taste bud. Comes right out of the book. So we're going to see the 3 types of cells that we talked about. So A is those basal epithelial cells. These are the ones that create new taste bud cells. These are the gustatory epithelial cells. These are the ones that are actually doing the job of receiving the chemical and starting the action potential on the cranial nerve there. C is the taste pore that comes in. That's where the chemicals enter. And D is the fibers of the cranial nerves that interact with these taste buds. And then we have these gustatory hairs here that kind of stick out and catch those chemicals. So each taste bud has somewhere around 50 to 100 epithelial cells, and this is what it looks like. So the it used to be 4, but now we have accepted 5 different basic taste sensations. So sweet tastes come mainly from sugars, as you know, alcohols, some amino acids are sweet, and lead. Salty tastes come from metal, from salts, from ions. Sour tastes come from acids. Acids always taste sour to us, and bitter tastes come from things that are very basic or very alkaloid. And most drugs, most chemicals, most poisons are very, very bitter tasting. And we're about 100 times more sensitive to bitter than we are to sour. This kind of seems backwards, but actually most poisons and the medicines are bitter, and so this is good that we're very sensitive to bitter. And then the last one is called umami, which is actually kind of similar to savory, which you would think of savory with eating a nice piece of steak or something like that. This was discovered by the Japanese. It's the newest recognized taste, and this is mainly caused by amino acids. Some other tastes that we can sense are minty flavors. So when you have some spearmint gum or some peppermint gum or a candy cane that has that mint flavor, what this actually does, this is not doesn't have to do with the taste receptor. This actually stimulates cold receptors in the mouth and actually makes your brain think that your mouth is cold. And spicy foods have a similar mechanism. There's a chemical called capsaicin, which actually lowers the threshold for the stimulation of warm receptors in your mouth. So even at a normal body temperature, your mouth thinks your brain thinks that your mouth is too hot because the threshold has been lowered by this chemical. And so then this can actually spread all over your body. If capsaicin goes around your whole body, and you can feel hot and start sweating all over your whole body, so it kind of tricks you into thinking that you're hot when you're really not. And that's the origin of the spicy taste. One thing to note is this tongue map is not true. I'm sure you guys have all seen this. You taste bitter in the back, sweet in the front, salty on the sides, sour on the back sides. This is not true. All of the tongue can sense all of these tastes. So we do have some individual differences in the way people sense taste. We have people called super tasters, and they have more of those fungiform papillae, and so they're more sensitive to taste. And this is people that might have tastes that are similar to children or to babies, even into adulthood. A chemical called naringin is found in grapefruits. It's a very bitter taste. But some people taste it as bitter, and some people don't taste it at all. And this is just a genetic difference in this, and some people don't have the receptor for that. And like I mentioned before, the number of taste buds that you have declines with age. So a little bit about the neurological pathway of taste. Taste can occur in 2 different ways. One is by direct depolarization. So a good example of that is salt. When you eat something salty, sodium is released from that food, and so sodium rushes into those cells that are those gustatory cells, and that creates an action potential, just like sodium would rush into a cell, a neuron, when you're trying to have a muscle contraction. Same idea. The sodium rushes in, that creates an action potential, and that stimulates it. So you have direct depolarization by the chemical itself. You also have many others that use the second messenger system, where the chemical starts a whole long chain of events in that neuron, which leads to an action potential later on. And so after that action potential occurs, we have 3 different cranial nerves that can be stimulated depending on where the taste bud was. So the facial nerve is kind of the anterior 2/3 of the tongue, glossopharyngeal is posterior 1/3, and then your taste buds in your pharynx and in your throat are innervated by the vagus nerve, number 10. So after you get that action potential on one of these sensory neurons, it's going to go to the medulla, synapse there, and then go to the thalamus, where most of our senses integrate except for smell. And then it's going to end in the gustatory cortex of the parietal lobe, right next to the temporal lobe. So that's the pathway for taste. So we're going to move on to smell. So the olfactory epithelium is where smell occurs, and these are specialized epithelial cells, and these are found in the superior concha of the nose. So that's all up in here. So the air comes in this way, and we have these little hairs sticking down, little neurons sticking down, and that's where the sense of smell comes from. It's a very small area. It's only about 5 square centimeters. And we have about 10 to 20 million olfactory receptors, so much more sensitive to smell than we are to taste, but still nowhere near the number of receptors we have in the eyes. One thing that's interesting is you kind of need a hairpin turn to actually get the chemicals up here where they need to go to get sent. So if you're just taking a light breath in, a lot of that air just completely misses the receptors. So when you really want to smell something, it's natural for us to take a hard sniff in, and the reason it does that is because when you do that, it kind of churns the air up, and a lot more of it interacts with the sensory receptors there, that allow you to smell it. So, and then there's, just like in the tongue, we have 3 different olfactory receptor cells, or olfactory cell types. I'm sorry. The first one is the receptor cell. And these are actually bipolar neurons, and these also get turned over pretty frequently too, not as frequently as in the mouth, but pretty frequently. About every 60 days, those cells need to be replaced, and this is very unusual for neurons. And these cells also have little hairs that stick off of cilia instead of microvilli, and these are in kind of a mucus. They're embedded in mucus, and this helps to dissolve the chemicals so they can be sensed by those neurons. And then we also have supporting cells. These surround the olfactory cells and provide some stability and shape. And then again, we have basal cells, which are the stem cells that are going to replace the olfactory receptors when they need to be replaced. And so here's a picture of the olfactory epithelium. And so just orient yourself. This is the cribriform plate of the ethmoid bone. Remember we studied that last semester. It had all those little holes in it. So you can see those olfactory receptor cells, their fibers go up through those little holes and interact with the olfactory nerve here, which is cranial nerve 1. So A is the olfactory bulb, which is the end of the cranial nerve 1. B would be those basal cells that are going to be there. The stem cells are going to be there to replace these receptor cells when they die. So C is going to be the receptor cells. You can see it goes down here, it has these little hairs, and it's embedded in mucus. So when the chemical comes up, it gets caught in the mucus, dissolves, and then interacts with these receptor cells. And then D is the supporting cell. So this is just like typical epithelial cells. They're just kind of holding this all together, giving it structure and shape. And then E is those olfactory cilia, which are actually receiving the chemicals. Okay, so we can detect about 10,000 different odors. This is much more complex and detailed than the smell sense, and then the taste sense. And actually, most of the food that we eat, we are heavily reliant on the smell of it to actually taste its full capacity, even though that kind of doesn't make sense. But to really enjoy food to its full, you have to have your smell intact. And so when you have a cold and you're trying to eat, food is just kind of tasteless. It's not because you're anything to do with your taste receptors. It's everything to do with the fact that you can't smell the food like you normally could. And so the neurons are stimulated by different combinations of a lower number of chemicals than 10,000, probably somewhere around 7 to 50. We don't really have an answer on that. But what this requires is called volatile substances, so substances in their gaseous state, and then they dissolve in that mucus, and then they're sensed by those receptor cells. So the pathway for smell is somewhat similar to what we talked about with taste, but a little bit different. So the molecule binds to the membrane of those receptor cells, the olfactory receptor cells, and this is always going to start a second messenger system. There's no direct stimulation like there is sometimes with taste. It starts the second messenger system, which is eventually somewhere down the chain of events going to open up ion channels, which is going to lead to depolarization of that neuron. And then the olfactory neuron stimulates the neurons of the olfactory nerve up in that olfactory bulb. That starts an action potential there. And then we have 2 different tracks, actually. One track is going to go directly to the olfactory cortex that's in the frontal lobe. And then another track is going to send the information to the hypothalamus. And here we can integrate emotional responses. And then as well, it's also going to go to the limbic system, which this is where we can associate smells with memory. So smell is tightly linked to memory, and this is because it goes through our hippocampus, and it can also elicit emotions. So if you were smelling something on a certain day that you also had very intense emotions, then it's very likely that next time you smell that smell, you'll also feel some of those same emotions, and you'll kind of have that nostalgic feel, and that has to do with the pathway of the smell sense. One thing that's really interesting is your right nostril has more emotional connections than your left, and so that's just the way it is because of the tracks of that olfactory nerve. So you get more emotional connections with your right, and your left nostril actually you get more accurate smell perception because you don't have as many emotional connections with it. And so there are some individual differences with smell as well, and so cilantro is one of those. So people that can't smell genetically just don't have the right receptor to smell cilantro, the chemicals in cilantro. It tastes like soap to them. And so there's probably a lot of people in the class that don't like cilantro, and it might say it tastes like soap, and it's probably because you can't smell it. So people that like cilantro usually like it because of the smell, not anything to do with the taste. There's another chemical called ethyl mercaptan, and this is the chemical that's actually put into liquid propane to make it smell, so it can be detected when there's a leak. Liquid propane doesn't have a smell naturally, so they put that in there as a safety precaution in case there is a leak. Then people can smell it, but it smells kind of like garlicky, almost like rotten eggs. But the problem is genetically some people can't smell it, so that doesn't help them. But that's it. So there's also an aging decline with smell as well, very similar to taste. The older we get, the less acute our sense of smell is. And then a condition called anosmia is the definition of that is a loss or reduction of the smell sensation. This can be a congenital thing that you're born with, and this is due to underdevelopment of those olfactory bulbs that have all the olfactory neurons in there. It can also be caused by trauma to the face. So if your cribriform plate gets crushed, then you can have damage to some of those neurons, some of those receptor cells, and that can make it so you can't smell. That can be temporary or permanent. Also, breathing in toxic chemicals can destroy some of those basal stem cells, and that means that no new receptor cells are able to be created. Another interesting thing is zinc is very important for the smell receptors, and so if you have a deficiency, you might not be able to smell, and this can be easily corrected by supplements. Also, some of these neurological disorders that we talked about last time can lead to anosmia as well, and especially some psych medications can lead to anosmia, and that's just one of the side effects of some of those medications.